All right, we're going to solve problem 1.29. So calculate the line integral of the function. The vector function is given x squared x hat, 2yz y hat, and plus y squared z hat. From the origin to the point 1, 1, 1, so it's in 3 dimensions, by 3 different routes. So the routes are given. Let's do part A. Part B is, I believe, kind of similar, so I'm not going to repeat that. Part C is interesting. That's direct straight line, so we can do that. So let's solve this problem. So what do we have? We have this x, y, z origin. And then I'm going to go to 1, 1, 1 in this following way. First 1, 0, 0. So here, that's 1, 0, 0. Okay. And then from that to 1, 1, 0. So that would be 1, 1, 0. Okay. And then from there, I'm going to go up to 1, 1, 1. So if this is 1, so I'll go up to 1, 1, 1. Okay. Something like this. Okay. So that's my 1, 1, 1. This is obviously 1, 1, 0. All right, so we're going to take that integral. I mean, it's a path integral, so I have 3 different segments. So for each of them, I need to evaluate, well, from 0, 0, 0 to 1, 1, 1, v dot dl. Okay, that's the question. And v is x squared x hat to yz y hat plus y squared z hat. Now, we call this number 1. This is number 2. This is number 3. So for number 1, what is dl1? Okay, it's along the positive x direction. So it's dx x hat. So if I do v dot dl1, I care only the x component. So that's going to bring me x squared dx. Okay, so let's see if there x goes 0 to 1. So x is 0 to 1. Okay, that's the only thing I need to know. So let's go to 2. That's parallel to y-axis. So it is dl2 is dy y hat. All right. So, and it happens on the xy plane. So when I do the dot product v dot dl2, it's going to be 2yz dy. Well, 2 things. Y 0 to 1, but z equals 0, right? Because it's on the xy plane. So this is automatically 0 because z equals 0. Number 3, we are going now parallel to z axis. So dl3 is dz z hat. So v dot dl3 y squared, okay, and dz. Okay. So now we have z goes 0 to 1. And what is y equal to? Well, y is constant here, right? It's 1. Basically, we have y equals 1. Just go up, changes only in the z variable. So y becomes equal to 1. So what you have here is just dz. All right, let's put it all together. Now, 1 x squared dx, right? That's what I have, plus 2, well, that's 0, plus, okay, this is the total, 0, 0, 0, 2, 1, 1, 1, v dot dl equals 2, and then the 3, that's going to give me just dz, right? So this, I don't worry, like here, 0 to 1 x squared dx, plus here, 0 to 1 dz. Pretty easy integrals, right? So let's move a little bit. This is x cubed over 3, evaluated 0 to 1. This is z, evaluated 0 to 1. This is 1/3 plus 1, which is 4/3. All right. Now we're going to do part C, which is the direct path from the origin to 1, 1, 1. Well, in this case, we can use the general form of dl in Cartesian coordinates, which is dx x hat plus dy y hat plus dz z hat. Now, I need to then find v dot dl. Remember, our function is x squared x hat, 2yz y hat, y squared z hat. So it's going to give me x squared dx plus 2yz dy plus y squared dz. Now, if I want to integrate this, well, I know all these variables change, right? X goes 0 to 1, y goes 0 to 1, z goes 0 to 1. But in order to integrate, I need to express, I think, these variables in terms of each other. Then it will simplify the integral significantly. So in this case, I'm pretty lucky because it's a very symmetric case. It's the, if you think about a unit cube here, it's along the diagonal. So they change, x, y, and z change this with the same rate, right? So that allows me to write dx equals dy equals dz. You can also think of it as like, if we want to parameterize these variables, x, y, and z in terms of some other variable, say u, well, what would you write? I mean, in this case, okay, you would say u goes 0 to 1, and then between these 2 points, all of them change the same way. You would just say x equals u, y equals u, z equals u, right? And as a result, dx, dy, dz all will be equal to du. So this also tells you how you would approach this problem if it wasn't a simple case like this. So if it was going to another point like 2, 1, 1 as opposed to 1, 1, because in that case, z would change, you know, twice as much as the other two variables, then you would write z equals 2u. Okay, so that's how you would do this. All right, so if all of these are equal and the variables change the same way, so my v dot dl becomes simply x squared dx plus 2x squared dx plus x squared dx, really, right? So if you add them all together, that 4x squared dx, right? And x goes to 0 to 1. So in that case, we could just do the integral 0 to 1, 4x squared dx, which is 4x cubed over 3, 0 to 1, which is 4/3. Part D here is obvious. It says, what's the line integral around the closed loop that goes along path A and coming back along path B? Since you're coming back to the original point, right, you're creating a full loop, you just need to look at the values you obtain, you know, in those two paths. You know, I didn't do part B explicitly here, but it also gives you 4/3. So you go along one path coming back, that means 4/3 minus 1/4, you're going to get 0 around the closed path. Okay. All right. I hope you enjoyed the solution.